Right, we're going to start our second set of notes for this unit called Buffers Made Easy. And I think I've mentioned before that this is probably the most difficult unit for most people, and this part of it especially. So first of all, we need to know what a buffer is and what it does and how it does it. A buffer is just really a case of common ion effect, if you can remember that from when we talked about Le Chatelier's law. So buffer basics. A buffer is a solution which resists changes in the pH when small amounts of acid or base are added. If you add large amounts of acid or base, then you're just going to overwhelm the system. But if you're talking about small amounts, so like our body, that it maintains a buffer system. You'll see these different diets where they say you need to change your pH or drink alkaline water or something like that. And the reality of it is that our bodies, our biological systems have built-in buffers that help keep us around pH for about 7, our homeostasis, and we can drink what we want to if we say it's the alkaline water, but it's not really going to change our pH much. So we're trying to set up those types of systems when we talk about a buffer. So a buffer can consist of a weak acid and its conjugate base, also known as its salt. So that example of that would be hydrofluoric acid. That's a weak acid. If I put it in water, then it would have H3O plus F minus. So hydrofluoric acid is my weak acid. And then over here, the fluoride would be its conjugate base. So if I also had NaF mixed in with that, it's going to ionize into Na plus F minus. So this salt would give us another source of that conjugate base. So that's what we're talking about, the common ion effect. So then whether we added an acid or a base to that, it would have many different things that it could react with to try to resist a change in pH. Same thing here, a buffer can then consist of a weak base and its conjugate acid, also known as its salt. So ammonia, a weak base. Combined with water, I have my hydronium ion. So NH3 would be my weak base. My NH4 would be my conjugate acid. And the same thing if I had this salt, ammonium chloride. This was a group 1 metal, the sodium, which always ionized 100%. Same thing, ammonium was in our solubility rules, one of the things that always ionizes 100%. So that's going to break down into my NH4 and my Cl minus. And once again, this NH4 is just going to be another source of that conjugate acid. So that's what we mean whenever we say that the salt is its conjugate. It's because within that salt, when it ionizes, it's going to either contain the conjugate acid or the conjugate base of those weak acids or bases. Buffers keep pH from changing drastically. Like I said, with small amounts of strong acids or strong bases are added. If a strong acid, and you'll see as we go in these notes, instead of really writing the acid each time, we're just going to put it as H plus, because that's really the part that we're concerned with. That's going to be the part of the strong acid that's going to change the pH. The anion part is just going to come along as a spectator. So if a strong acid is added to the basic part of the buffer, is added, the basic part of the buffer will react with it to produce a weak acid. So here's my weak base. If I add a strong acid, so that's a source of hydronium ions, it'll just react to give me the conjugate, the conjugate acid, which is still a weak acid. So the pH would just drop slightly. Or I could also look at that using my other example of HF. If I had the strong acid, add it to my F minus, which we set up here was a conjugate base, then they're going to react to form HF, which is a weak acid. So once again, the pH would only drop slightly. If a strong base is added, and once again, we're just going to put hydroxide for our strong base. That's the part we're interested in. The cation tags along as a spectator ion. It's added to the acidic part of the buffer. If it's added, the acidic part of the buffer will react with it to produce water and a weak base. So once again, this is representing my strong base. If it reacts with the hydrofluoric acid, which would be the acidic part of the buffer, then we're going to end up having water. And then in this case, the fluoride ion. We're only going to have a slight increase of pH as compared to what would happen if we did not have a buffer. Or we can also do the same thing with our other example. If I had my strong base and I added it into a buffer system that was made with my ammonia and its conjugate acid. So now this is a base, so it's going to react with the conjugate acid part. And it's going to end up forming H2O and then a weak base. So once again, a slight increase in pH, but not a huge change. So the whole point of a buffer system is for there to be different entities in there that can either handle an addition of H plus ions for something that's acidic or hydroxide ions for something that's basic, and can kind of tie up those ions or change them into water, have them react so they'll change to water, but something so there won't be a drastic change in the pH whenever they're added. Buffers cannot contain strong acids or strong bases, because if you remember, strong acids and strong bases ionize almost 100%. So if I add something into it, those things want to be ionized. They want to exist as ions. So they have no reason to react like with the hydroxide or with the hydronium ion to give us something more neutral. So those cannot be part of a buffer that is made, but sometimes they may be made by the reaction of a strong acid or base with a salt. So sometimes it may be made in that process. All right, so let's first of all look at if I'm adding a strong acid to a buffer. And once again, we're going to start saying if we're talking about strong acid, instead of writing the strong acid out, we're just going to represent it with my H plus. So the strong acid will react with the base. And it may be a conjugate base. We're using kind of those words interchangeably in the buffer to produce a weak acid. The weak acid then will only lower the pH slightly as compared to lowering it a whole bunch, what you might expect if I have a strong acid. Another way to think of this is that the strong acid, the H plus, changes one part of the buffer into the other. And in this case, if we were looking at a buffer system made between acetic acid and its salt, then the acetate would change back into the acetic acid, which is a weak acid, so not a large lowering of the pH. And as I've kind of already mentioned, if we're looking at strong acids, we're kind of just going to write them as the H plus ion rather than the whole thing, since it's actually what we're interested in. So if I set up a buffer between acetic acid and sodium acetate, that's its salt, then I'm going to have floating around in this, I'm going to have acetic acid. I'm going to have some sodium, because that's what this is going to ionize to. Group 1 metal and also acetate. They both always ionize 100%. C2H3O2, that's my acetate ion. So C2H3O2 is my base. This was my weak acid. This was its conjugate base. So that's the base that I have available in this system, and then to be a spectator ion. So now if I add some strong acid, because that's what we're saying that we're going to do here, the acid's going to look at everything it has, and it's going to say, oh, this is what I want to react with, because that's the base. So an acid wants to react with the base, so it's going to react with the acetate ion and go back to forming acetic acid, which is a weak acid. So it does not ionize 100% in solution. So we'll have a slight decrease in pH by adding that strong acid, because we did form a weak acid, but not a large decrease in the pH. Now let's see if we add a strong base to a buffer. And once again, when we're talking about strong bases, instead of writing the whole thing, we're going to write the hydroxide ion, because that's what we're interested in. The strong base will react with the acid, or it could be the conjugate acid, but that still would be the acid that would be present to produce a weak base. The weak base will only raise the pH a slight amount as compared to what you would expect a large change in pH when you added a strong base. So another way to think of it, just like we did on the other situation, is that the strong base changes one part of the buffer into the other. And in this case, it's going to be the ammonium ion is going to get changed back to ammonia. So when writing these reactions, once again, I think I've already said that, instead of strong base, the whole thing, we're going to be putting OH hydroxide. So now if I have a buffer of NH3 and NH4Cl, then around here I got NH3, I've got Cl minus, I've got NH4 plus. Those are all the things that I have floating around in that water. On both of these, when I'm saying what's available, I'm leaving out, the water aspect of it, because we want something that's going to react with either the hydroxide or the hydronium. So this is my base, this is my conjugate acid, this is my spectator ion. Okay, so that's what I got floating around in there. So my acid available is my ammonium, my base available is my ammonia. So no matter what I add, there's something to react with it and to try to minimize that pH change. So in this case, we said we were going to add a strong base. So I'm adding a hydroxide. And once again, it's going to look around, see everything that's available. And it's going to say, oh, wait, I'm a base. I want an acid. That's what I want to do. That's what I want to react with. That's what I fit together. So it would react with the ammonium. And you would end up getting back your ammonia, which this should kind of be scooted over. That WB should go under here. I would end up getting back my ammonia and then water. Once again, ammonia is a base, but it's a weak base. So just a slight change in the pH. All righty, let's see where we're at. Sorry, y'all, my nose is stopped up. I know it doesn't sound good when I'm trying to teach something. All right, so what happens if I have more moles of H plus or OH than the buffer component can handle? So if the number of moles of either of those exceeds the number of moles of the buffer component, then they would react. All that part of the buffer would be consumed or reacted, and then you would end up with some excess hydrogen ions or hydroxide ions, because there would be nothing to handle them or to react with them. So then you would see a lot larger change in pH very quickly. You would say the buffer capacity had been reached. Excuse me. How do I make a buffer? If asked to choose the components to make a buffer at a given pH, you want to look at the Ka values of the weak acid or Kb values if it's a weak base. And when you want to choose a combination of acid conjugate base that has a pKa very close to the desired pH of the buffer, the concentration of the two components can be adjusted to get the desired, I'm sorry, to get the desired exact pH that you're looking for. So just like we said that pH is given to me by the negative log of the hydrogen ion concentration, the same thing. If I want the pKa, I would take the negative log of my Ka value. So a lot of times you're given a Ka value, you can figure out what a Ka value is given enough information. So if you take the negative log of that, that's going to give you your pKa, and you want that to be as close to the pH range that you're wanting your buffer to exist in. And I think we'll do a problem in a little bit that'll make that a little bit more clear. So just to kind of reinforce some things, we know that our conjugate acid base concept. Remember my definition, Bronsted Lowry definition, and acid is going to be a proton, or which H plus donor, and a base would be a proton or H plus acceptor or accepts. I'm not sure if that's right English there, right? But anyway, so if I have an acid on one side, it's going to have a conjugate base on the other. It's lost a hydrogen. If I have a base as my reactant, it's going to gain a hydrogen. And then on the other side, I'm going to have its conjugate acid. pH is equal to the negative log of the hydrogen ion concentration. This relationship that we used just in the other video comes in handy. And at 25 degrees Celsius, you know that Kw is equal to 1 times 10 to the negative 14. All right, and usually you assume it's 25 degrees Celsius unless given other information. You also need to realize that any titration involving a weak acid base is a buffer problem. If I titrate my acid, this would be my weak acid with sodium hydroxide, then as soon as I put in that first drop of sodium hydroxide into the container, it's going to, the sodium cation is going to combine with the anion of my acid. And then once again, because it's sodium, which is a group 1 metal, is going to then completely ionize. So these are the two formulas that can be used to solve buffers. This one is called the Henderson-Hasselbalch equation, and that is on your formula chart. This is the one that I'm going to work my problems with. It's not on the chart, but it's an easier way, I believe, to work the problems. And it's pretty easy to memorize. You would have to memorize that. It's not on the green chart. So your hydrogen ion concentration is going to be equal to your Ka times the concentration of your acid divided by the concentration of your base. That was a little bit easier to use and pretty easy to memorize. But I can tell you this, that I have had students that have chosen to use this formula. I've worked the problems one way, and then when they've done their practice, they've chosen to use other formula. So that also is just fine. That seems to work for you. All righty. If an acid is added to the buffer, simply add acid to the numerator, because our formula is, just rewrite it, plus is equal to Ka, my acid concentration, base concentration. So if acid is added, then I need to add acid to the numerator, and I need to subtract that same quantity from the base. Since it's self-sacrificing, and part of it was used to neutralize the acid. If a base is added, it's just going to be the other way around. I'm going to add to my denominator because I'm adding base, and I need to subtract from my numerator because part of the acid would be used to neutralize it. This is kind of something different than we've been doing. Whenever you're adding or subtracting, it needs to be in moles, not molarity. And to get your moles, you're going to take your molarity times your volume. And we've been doing that. Our volume has been in liters. And in a little bit, I'm going to introduce something called millimoles that makes this a little bit easier, just the math easier to work with. But this just may be a quick thing that you need to remember. When equal concentration or moles of acid and base are present, which occurs at the half equivalence point of a titration, and we'll talk a little bit more about that. The ratio of base equals 1, and therefore pH equals pKa. So once again, if we go back to this this formula, we're saying if A over B, if the concentration, if that is equal to 1, then it's going to cancel out. And then I'm going to have H plus concentration is equal to my Ka. So same thing, I would take the negative log of each of those, and that's where I'm going to get my pH is equal to my pKa, which can become pretty handy, especially when we start talking more about titrations. So as we mentioned before, and we'll do an example in a minute, if you're asked to construct a buffer of a specific pH and given a table of the Ka's, choose a Ka with an exponent close to the desired pH and use equal concentrations of the acid and the base. All right, so let's try and look at some of these. So the Ka of formic acid is 1.8 times 10 to the negative 4, and formic acid is HCOOH, weak acid. H plus COOH, and the Ka for that reaction is 1.8 times 10 to the negative 4. So it says calculate the pH of a 0.5 liter of buffer solution composed of 0.5 molar formic acid and 0.7 molar sodium formate. So that's the other thing I have in here. I have sodium formate, which I need to recognize that it's going to ionize, and it's going to be a source of the conjugate base. This is my acid. This is my conjugate base. This is a source of my conjugate base. Once again, just Le Chatillier's law. If I increase that common ion, it's going to push it back toward my reactants. But in this case, what we're more interested in is we have something to handle whether we add acid or whether we add base to it, we have something to handle those. All right, so calculate the pH. And I said that, and then after, so we're going to have to do two problems here. One, the pH at the beginning, and then after we add 10 mils of a 1 molar hydrochloric acid solution. So to begin with, so we're going to do before or at the beginning, and I'm going to be using this formula. So if I want my pH, I need my hydrogen ion concentration, Ka, acid, base. Okay, so my H plus concentration is going to be equal to 1.8 times 10 to the negative 4. And then for my acid concentration, it said that I have 0.5 molar. And then for my base, I don't have a strong base, so you have to remember you're looking for your conjugate base. So my conjugate base is coming from my sodium formate. So it's going to be 0.70 molar. Remember, this is formic acid, a weak acid, so it's not going to ionize 100% here. So that's why I have to have the salt. I need another source of that conjugate base. So they don't form a buffer. It'll have something that can handle the hydroxide ions, and it'll have something that can handle any hydrogen ions. All right, so I get my H plus is equal to 1.29 times 10 to the negative fourth. And like I said in the other video, I'm going to show all my work, even though it doesn't seem that I should have to. pH is negative log 1.29 times 10 to the negative fourth. So I get a pH equal to 3.89 with 2 sig figs, because both of my concentrations had 2 sig figs. All right, so that was the easy one. So now we need to think about what is happening after I add my 10 mils of hydrochloric acid. All right, so since we're going to have to be, we're adding an acid. So we're going to add to our acid and we're going to subtract from our base. But we can't add and subtract in molarity. This is when we have to add and subtract in moles. So if I look at this right here, I'll change that milliliters to liter, although in a minute I'm going to show you something you can do instead. So that becomes 0.01 times 1. That tells me that I'm adding 0.0 moles of H plus. So that's how much I'm going to add. I know my sig figs are not right there, but I don't want to go to all that trouble or mess to write them out. So I'm going to fix my sig figs at the end. So now I need my acid concentration. So I need moles per liter. So if I look at how many moles I originally had, I had 0.5 liters and my molarity was 0.5. So I'm going to say 0.5 times 0.5. That was how much I had originally. And then I added another 0.01. So that tells me how many moles. And then I need to divide that by liters to get it in molarity. So here I had 0.5. And then here I added a 0.01. So I ended up with, if I take this, divide it by this, I end up with a 0.51 molar. That's my acid. All right, now we're going to do the same thing for our base, but instead of adding it, we are going to subtract it. So for my original amount of my base, it says that I have 0.5 liters of 0.7 molar. So that's going to be my 0.5 times my 0.7. So that will get it into moles. And then if it's the acid, I had to add it to my acid and subtract from my base. And then the liters, the volume would be the same. 0.5 originally, and then I added 0.01. And if I do that calculation, I end up with 0.67 molar. All right, so now we can fill in our formula. H plus is equal to my Ka, which is 1.8 times 10 to the negative 4. And my acid, my new acid concentration, divided by my new base concentration. And when I put that in my calculator, I get 1.38 times 10 to the negative 4th, and that's my H plus concentration. So we wanted our pH. So I'm going to say pH is equal to the negative log of 1.38 times 10 to the negative 4th. And I end up with a pH of 3.86. 2 sig figs because my concentrations up here had 2 sig figs. This one had 3, but I'm going to be guided by these that had 2. So this side, not so bad. This is new. And like I said, probably the biggest thing is that you need to, since you want molarity, you're going to have to change that to moles since you're either adding or subtracting some amount. If you add an acid to the buffer system, you're going to add your new moles to the acid, which would be your numerator, and subtract your new moles from your denominator. All righty. All right, let's see what we got next. I have some notes on the bottom of that page, but I think we'll do them later. Sorry about that, y'all. Got a little bit. All right, so preparing buffer solutions, you want to use a 0.1 molar to 1 molar strength of reagents of your acid and your salt, or your weak base and your salt, and choose a Ka that is near the hydronium concentration you want. The pKa, which I said is just a negative log of the Ka, should be as close to the pH desired as possible. And then you adjust the ratio of your weak acid to your base as you need it to kind of fine tune your pH. If you didn't watch the video I posted about estimating pHs, that would be helpful to go back and watch that, because it can come in handy whenever you're doing this, whenever you're trying to kind of match them up. All right, using an acetic acid sodium acetate buffer solution, what ratio of acid to base will you need to maintain a pH of 5? Explain how you would make up such a solution. All right, so we're looking at acetic acid. So that's my weak acid. H3O2. So this is my weak acid. This is my conjugate base. And then it also said that I've also added sodium acetate, which sodium is a group 1 metal. So this is all, and the acetate too, both of those were ions that are always going to ionize. Sodium becomes a spectator, and this becomes a source for your conjugate base. All right, so let's work at this. I know I want my pH to be 5. So since I'm going to be using the same formula we did earlier, which would be your H plus equal to your Ka acid base. So this is what we're looking at, because it's asked us to look at the ratio of acid to conjugate base. So that's really what we're interested in. But I need my H plus concentration. So I'm going to say my H plus is equal to 10 to the negative 5, because it's 10 to your negative pH. So when I do that, I get that my H plus is going to be equal to 1 times 10 to the negative 5th. So once again, if you're estimating, if you have a pH of 5 with no numbers behind it, or a pH of 4, of a pH of 10, and without any numbers, with those just being 0, that's always going to be your exponent's always going to be 1 times 10 to the, in this case, negative 5th. If this pH would have been 11, then it would have been 1 times 10 to the negative 11. So before I got up to a pH of 6, if I was trying to figure out what this was going to be, if let's say I had a pH of 5.5, it's still going to be to the negative 5. This is going to be the number that's going to be changing, because it's just going to get a little bit larger, and then it wouldn't get up to 10. I'm going to get a little bit smaller. I'm sorry. And it wouldn't get up till 10 to the negative 6, or down to 10 to the negative 6 until you got to pH of 6. I didn't explain that very well. Like I said, go back and watch that video about estimating pHs and see if you have any questions on that, because it'll come in handy. Okay, carrying on. So I'm going to say 1 times 10 to the negative 5th is going to be equal to my Ka, which was given to me, or maybe not, but the Ka for acetic acid is equal to 1.8 times 10 to the negative fifth. So that's going to be 1.8 times 10 to the negative fifth acid divided by base. This is what I'm interested in, so I need to bring this over and divide by it. So I get 1 times 10 to the negative fifth divided by 1.8 times 10 to the negative fifth. These is equal to my ratio. So these are both 10 to the negative fifth. They can cancel out. So this would be my ratio. I need 1 mole of acid, for every 1.8 moles of base, and mix with enough water to dissolve. So on these type of problems, they usually give you some numbers that are easy to work with, where you have these exponents that can cancel out, making it a lot easier. I mean, they could take this question all the way up to like, how do you actually mix it? If you knew what the acid was and you knew what the base was, so you could figure out what the conjugate base was, and so you could figure out their molar mass, and you could figure out exactly how many grams you would need, because that's a more realistic way to mix things, or to mix things to use in a lab. So this could go some different ways, could kind of go into a more extensive problem, like an FRQ type of problem. All right. If the relative number of moles of the acid conjugate base or base conjugate acid, that is important because they are in the same solution. So the volume isn't the difference. So when we're talking about molarity, the denominator part, the liter part, is the same for both because they're sharing a common container. They are in the common amount of volume. So what becomes important is how many moles you have of each one. And so this allows companies to make concentrated solutions of buffers, and then the customer can dilute it. And that's not going to affect the number of moles present. It's just going to dilute those moles. It's just going to change the volume. All right, so let's look at one if we're given a KB instead. So I have a buffered solution of 0.25 mole H3. So it's a base. So I have NH3 plus water. So there's my base, my weak base, and I end up with NH4. That's my conjugate acid plus some hydroxide. And then I have, once again, my ammonium chloride, my salt, and this I need to recognize that it is the source of my conjugate acid. Because once again, this is a weak base, so this reaction doesn't go forward a lot like a strong acid or a strong base. So I need another source, or a main source actually, for my conjugate acid in this case. And so for this reaction, my KB is equal to that. But if we're using that formula that we have been using, because we still want to find pH, so at some point we're going to have to get the H plus concentration, then I really need my Ka. So now we're going to go back to what we did earlier, where we said Ka times Kb is equal to Kw, which is 1 times 10 to the negative 14. So if I rearrange this, I can say Ka is going to be equal to my Kw divided by my Kb, which is what they gave me. And I end up with 5.6 times 10 to the negative 10. All right, so now we should have what we need. This one isn't going to end up being that bad of a problem. Trying to get to my pH, so I need my H plus, so it's going to be my Ka. And then my acid, remember it's really a conjugate acid. That was my 0.40 molar. My base was my weak base, and it was 0.25 molar. So when I do that, I get my H plus concentration is 8.9 times 10 to the negative 10th molar. Once again, pH, I'm not just going to all of a sudden write down a pH number. I'm going to say pH is equal to negative log of 8.9 times 10 to the negative 10th. And that gives me 9.05 to sig figs, which is what I needed. And if we go back and we look at this, we said we were starting with a weak base. So it makes sense that my pH should be on the higher side of 7 because it is made out of a weak base. So just kind of a double check. All right, and then calculate the pH when 0.1 moles. Nice, they already put it in moles, so I don't have to do that. Of gaseous hydrochloric acid is added to 1 liter of the buffered solution. So this is a strong acid, so I'm going to need to add it to the acid component and subtract it from the base component. So for my acid, to begin with, I had, remember, it's going to look different because it's actually my conjugate acid. It's my NH4. It says right here I had 1 liter of it, so that means it's a little bit easier to get it into moles. So that means I had 0.4 moles to begin with, and then here I added 0.1 moles, and then my total volume was 1 liter. If you notice, it said I added 10 moles of gaseous hydrochloric acid. So that's why this one didn't change from what I had originally. So that gives me a 0.50 molar. And then down here, my base, same thing. My base is my ammonia. And so we had 0.25 moles because once again, 1 liter. I added an acid to it, so that means it's going to have to sacrifice 0.10 moles to react with that acid, and it was in 1 liter. So here I get 0.15 molar. All right, now I should have everything that I need to finish that out. H plus is equal to my Ka, which was 5.6 times 10 to the negative 10. Acid concentration 0.50 molar divided by base 0.15 molar, and I get an H plus concentration of 1.85 times 10 to the negative 9. Once again, I'm going to say this number is equal to my H plus concentration. I'm not just going to leave this number floating around without it meaning anything, because that's not going to get you any credit. Negative log of my 1.85 times 10 to my negative 9 is going to be equal to my pH. So that gives me pH is equal to 8.732 sig figs because my concentrations up here had 2 sig figs. So once again, don't get confused, because when you're doing a buffer, and you're looking at acid over base, if you know you have a weak acid, then that means your base is really your conjugate base, and that comes from your salt. If you have a weak base, like we did here, we had ammonia, a weak base, you should be able to recognize that as a weak base. And those 2 others that we talked about earlier, okay? If you have a weak base, then this is your base, and then your acid is actually your conjugate acid. And once again, that is coming from your salt. Just a little reminder right there in case you're having trouble following that, because I'm not getting, I mean, it's a lot of stuff and it can be confusing. All righty. Back there, and so this will be kind of what we talked about, where we said try to, if you're asked to set up a buffer solution. All right, a chemist needs a solution buffered at a pH of 4.30. And you could choose from the following list of acids. And they give us some. So once again, if my pH was equal to 4, then my H plus concentration would be equal to 1 times 10 to the negative 4th. And the reason I'm saying that is because you could just do all 4 of these and you could find your pKa, because really what you would like to do is you would like to say your pH is about equal to your pKa. But since you're always going to be in a time crunch, I'm saying, think about this. Is 4, if that was 4, it would be 10 to the negative 4th. I know it's not going to be 10 to the negative 5th because that number is closer to 4 than closer it is to 3. I'm sorry, or it's not, it's going to be, how should I say this? Sorry, hold on, guys. Phone's ringing. Grab this phone call real quick. Maybe. Hold on just a second. All right, where was I at here? All right, so like I said, you could take the time to do negative log of all those Ka values and see whichever one's closer to 4.30. Or, as I'm sure y'all have heard, in most multiple choice, there's a couple you should be able to kick out. So if this was just pH was 4, then it would be 1 times 10 to the negative 5th. If the pH it was equal to 5, then it would be, as I'm sure you guess, 1 times 10 to the negative 5th. So since I had a pH of 4.30, it's going to fall somewhere between those two. So right away, I can see that one and that one don't make any sense. Okay, so that leaves you just 2 that you would do the negative log of that Ka value. And when you did that, you would get 4.89 here. These are going to be pKa values. And for this one, you would get 4.19. 4.19 is closer to 4.30. So that means you would want to choose this one. Like I said, this is just estimating hydrogen ion concentration or pH concentration, vice versa. It's good to have on the multiple choice ones where you can't use a calculator. So please try to watch that video. So now we want to calculate the ratio of acid to base like we did earlier, required for each system to yield a pH of 4.30. So I have my pH, so from that I can get my H plus concentration. So that's going to be 10 raised up to my negative pH, so negative 4.30 tells me that my H plus concentration is going to be equal to 5 times 10 to the negative 5th. All right, so now if we use that formula, I'm going to have my H plus concentration, which is 5 times 10 to the negative 5th, is going to be equal to my Ka that I said we needed to use, 6.4 times 10 to the negative 5th, and my, all right, so as you can see, if you're looking ahead, because now I need to divide by 6.4, so I end up with 5 times 10 to the negative 5th, divided by 6.4 times 10 to the negative 5th is going to be my ratio I'm interested in. So if we did what we were supposed to, and we picked out the number where we have our closest, our pKa to our pH, then these are going to cancel out. And now I have a ratio of 5 moles of acid to 6.4 moles of base and enough water to dissolve. All righty. So talking a little bit about acid-base titrations. So in Chem 1, we did acid bases titrations where we had a strong acid and a strong base. And the pH at the equivalence point is equal to 7. So that's the one where we said strong acid plus strong base. Then that's where we could use that formula of MAVANA is equal to MBBBNB. And M was our molarity, B was our volume, and N was a number of moles. So for my acid, it would be your number of acidic hydrogen. And if it was a base, that would be your number of hydroxides. And this is ignoring coefficient. Now just remember, this only works if it's strong, strong. Okay, if not, then it's a lot more trouble, of course. So I think I did a little example problem here. If you want to jot it down, let's just say I have this reaction. Sulfuric acid plus sodium hydroxide is going to go in a neutralization reaction to produce sodium sulfate and water. My pH should be 7 because this is a neutral salt. It would require a little balancing, which really doesn't matter in these because when you're looking at your ends, you're not really worried about your coefficients. So I think though to balance it, I would need that and I would need that. So let's say that I had 10 liters of this acid and it was 0.5 molar. And I wanted to know how much of this base I needed if it was 0.25 molar. All right, so using this formula, the molarity of my acid would be 0.25 molar. Volume is what I'm trying to find. I did that backwards. Let's try that again. Let's do my acid over here. So that's going to be 0.5 molar. Volume is going to be 10 liters. Acidic hydrogen are going to be those two. And I set that equal to my molarity of my base times the volume is what I'm trying to find, and my hydroxides. Now don't worry about that too. So this is just one. So whenever I do all that, then I end up with a volume for my base of 42 sig fig liters. You can only use that for strong, strong. If I have anything else, my weak acids, my weak bases, the equivalence point is not going to be at 7, okay? So if I have a weak acid and a strong base, that means that my strong wins out my equivalence point. And if you look down here, jump ahead a little bit, the equivalence point is when the number of moles of acid equals your moles of base. Not the molarity, but the moles of acid equal your moles of base. If I have a strong acid with a weak base, a strong acid's going to win out. And then when I get to my equivalence point, then it'll be less than pH. In Chem 1, we talked about equivalence point and endpoint. They are different things. The endpoint is when you actually see the color change from the indicator. If you've made a good choice of picking your indicator, it should be changing color. So you should get your endpoint at the same where the equivalence point should be. That's if you've done a good job of picking that out. All right, let's see. I think this is the last thing. Nope, did I mess up again? No, I didn't. I did. All right. All righty, so let's look at this problem, okay? So before we do that, I want to talk about something that's called millimoles. So we said if I wanted to get my number of moles, then I would take my molarity times my volume in liters, and that would give me my moles. And that usually leads to your moles being in some decimal point. If I go instead for millimoles, I would still take my molarity, but I would multiply it by my volume in milliliters. Then that usually gives me my millimoles are usually going to be some whole number that are going to be easier to just do your math on. And so as you're working through these problems, a lot of times, especially if your volumes are being given to you, if you even see, if you continue to look down in milliliters, instead of moving your decimal back 3 places and maybe making an accidental mistake, it's just better to kind of work in millimoles, because as long as you're dividing it by milliliters, you're still going to get the same concentration at the end that you would if you were working in moles instead of millimoles. All right, so let's kind of work toward that. For the titration of 50 mils of 0.2 molar nitric acid, that's a strong acid, with 0.1 molar sodium hydroxide, strong base, calculate the pH at each of these different points. So first of all, we're going to be talking about before any sodium hydroxide. So we're just wondering at this point, at that point, then I am just going to figure out what my pH is. Since that is a strong acid, then to find my pH, I'm just going to take negative log of my concentration. So that's going to give me a pH equal to 0.699. What I'm also going to figure out at this point is how many moles of my acid I have, because this is all the acid I'm ever going to use. If you look down here through the problems, you're adding more base, but you're not adding more acid. So I really need to know how many moles I'm adding of, how many moles originally I had of that acid. So I'm going to look at my moles of my acid. I'm going to take my 50 milliliters times my 0.2 molarity, and that's going to tell me that I have 10 millimoles of H plus. That's what I start with and doesn't change. All right. So now we're going to add 10 mils of sodium hydroxide. And up here it said that sodium hydroxide was 0.1 molar. So if I want to look at my millimoles, I'm going to say if I have 10 times 0.1, that's going to say that I have 1 millimole of my hydroxide added. That's what I got when I added 10 mils. 1 mole of that. I'm still trying to get my pH in all these. So let's think what's going on. Hydrogen plus hydroxide is forming water. These are strong acids and they're strong bases. So the sodium and the nitrate are just spectator ions in this. So I have 10 millimoles of this from the beginning. That never changed. Now I added 1 millimole of my hydroxide. Excuse me. This is a 1-to-1 ratio, because if we looked up here, this is only 1 acidic hydrogen and my hydroxide is only 1 here. So a 1-to-1 ratio. So that means this is my limiting reactant. So in other words, all that's going to get used up. So this is going to be -1, -1. So I end up having 0 here, and here I have 9 millimoles of my acid left. And that's what I'm interested in. So to get my acid concentration, it's going to be my 9 millimoles that have not reacted yet. So this is millimoles divided by milliliters instead of moles divided by liters. milliliters, I had 50 to start off with, and I added another 10. So a total of 60 milliliters, which is going to give me 0.150 molar. And then I take the negative log, and that's going to give me a pH of 0.824. All right, so that's what happens first. So then we said we're adding another 10 mils because it said 20 mils total. So we're adding another 10 mils of that 0.1 molar sodium hydroxide. So I need to figure out how many millimoles that is. So I have 20 times 0.1 tells me that I've added 2 millimoles total of hydroxide. So once again, if we think about it, I'll do this one more time, and then I don't think I need to do it every time. I started off with 10 millimoles of this and 2 millimoles of this. This is still my limiting reactant. -2, -2. So 8 millimoles is what I have left. This became 0. I'm trying to find my pH, so I'm interested in my H plus concentration. I have 8 millimoles left. I need to divide that by my volume. 20 mils. No, it's not additional, that's total. So 20 mils of my base added plus 70, plus 50 would give me 70. And then that means that I would get a H plus concentration of 0.114 molar. Once again, I'm making sure that I show what this number goes to. I need the pH, so I need to do negative log of 0.114. So that's going to give me a pH of 0.942. All right, and then we're keeping on. We're adding more and more. Okay, so now we have 50 mils of my sodium hydroxide. So 50 times 0.1 tells me I have 5 millimoles of my base added. So originally I had 10 moles of my acid, 5 millimoles of my acid need to react with this base. So that means I have 5 millimoles of H plus left at that point. My volume is going to be 50, and I started off with 50, so divided by 100, and then I'm going to end up with an H plus concentration of 0.0500. Negative log of 0.05 is going to be equal to 1.30136 figs, and that is my pH, and I'm going to make sure that I label it there. All right, so here now I've added a total of 100 mils of the sodium hydroxide. So 100 times 0.1 tells me that that's going to be 10 millimoles of my hydroxide. So at this point, I have 10 millimoles of my hydroxide have been added, and I originally had 10 millimoles of my acid. So moles are equal to each other. This is my equivalence point, and for a strong, my pH would be 7 point, how many sig figs? 3 sig figs, 0.000. And I'm going to make sure that I include that, not just say pH of 7. All right, so now we've tipped the scales, and now we're going in the other way. Now I've added 200 mils of my sodium hydroxide. So 200 times 0.1 tells me that I have 20 millimoles of my hydroxide have now been added. So this one I am going to go ahead and write H plus OH minus gives me my water. So my H plus never changed from the beginning. I had 10 millimoles. Now by the time I've added all 200 of that, excuse me, I'm sorry, I have 20 millimoles. So now that means that my hydrogen ion is going to be my limiting reactant. All of it's going to be used up, and I'm going to have extra of my hydroxide. So that means when I calculate my pH, it should be greater than 7. But so I'm going to subtract 10. So I end up with 0 here, subtract 10. I end up with 10 millimoles of my hydroxide divided by my total volume. 200 and the 50 that was originally in there is going to be 250. And so when I do that calculation, I end up with a hydroxide, not a hydrogen concentration, a hydroxide concentration of 0.0400. So what I need to realize, because my question is, what is the pH? Is from here, I'm going to have to get the pOH first. Negative log of 0.0400. Excuse me. And that is going to give me a pOH of 1.398. Sorry, I'm having trouble reading my writing. So then to get my pH, I'm going to take 14 minus 1.398. So that means my pH would be equal to 12.602. 3 sig figs, and it makes sense because at the end I had extra hydroxide. All right, I think that we will stop there. That gives y'all a lot to do. And please come with questions because we're going to be moving along. I'm getting a little panicked because I feel like we're running out of time. Always get panicked right about now because I want us to have some time to review. Okay, see y'all on Tuesday. Sorry.